Okay, so let's start our lecture today. So, uh, okay, so okay, so I think I didn't capture the right idea for the uh yeah, for the answers. So uh okay, so okay, so I'll just manipulate what the uh ChatGPT gives me. Okay. So this is the Taylor expansion of the log of 1 minus u, right? And then there's a so of course there is some other terms plus, sorry, it should be minus, right? Okay. So here so I think what he did, so yeah, so let me okay, so yeah, so let me erase this. So okay, so okay, so let's do that. So so here he says that for modulus u less than 1, okay, so we have that log of 1 minus u is equal to this Taylor expansion, where the log is just any, so let's say that the log is the principal branch, right? Where the log, so so in this case I can just define the log is from C take away the 0 to negative infinity, okay, to C, okay. Yeah, and we say that log of 1 is equal to 0 for the argument function. So so then so this is well defined because we are only define the u to be less than 1, so that it stays close to the right plane. Yeah. So nothing intersects 0. Okay. So here, so therefore, we have log of 1 minus u plus u plus u squared over 2 is equal to negative summation k equal to 3 to infinity of uk over k. Okay, so u to the kth power over k. Okay. Okay, so now, and then we denote this by the small little l of u. Okay. So we say it's the little l of u, which is being defined as this guy. Okay. Okay. So, and then okay, so now we fix k in C compact. Okay, so be a compact subset. And we let R to be maximum of Z in K modulus Z. Okay, so this is essentially the biggest, it is a radius that the disk of its radius will contain. So it's like the maximum radius of points in this compact subset. Yeah. And then, okay, so, and then, so there are only finite many lattice point satisfying the condition that the modulus of this omega is less than or equal to 2r, right? So yeah, so it is true. So so then he says that consequently after omitting finally many initial factors, we may assume that modulus of Z over omega is less than or equal to 1/2, where Z is in K. Yes, so we can do that, right? Because for large Z's, we know that, for large omegas, we know that the modulus of omega is actually bigger than 2r, right? So, and the modulus z is less than r, so we have that. So, okay, so now for these tail factors, we have 1 minus z over omega lies in the set the disk center at 1 of radius 1/2. Okay. Yeah. And then we have that yeah, and also this disk is lies on the right half plane, right? Yeah, so he is saying that we just use the principal branch, which avoids. Okay, so which avoids the let's say the negative ray, right? 0 to negative infinity. Okay, sorry, I think I made a mistake here. So this cutting should be made at 0 to negative infinity. So it's like the negative real axis to C. Okay, such that the initial angle, the angle log of 1 is equal to 0. So it's like the angle at the positive real axis is chosen to be 0, and then the angle might be the angle goes up, like up to pi in the upper half plane, and then goes to negative pi. Okay. Let's say that it goes to let me use the notation real cross the okay, so negative pi to pi. Okay, so okay, so then he says that so for modulus u is less than 1/2, we have so the modulus of L of u is which is equal to the modulus of this guy. So here I just ignore the negative sign. UK over K, so which is less than or equal to the sum okay. Modulus u to the kth power over k. Okay. So there's one thing that going on here is that so this is a convergent. So this theory is like a yeah, so this theory is actually converging if we apply the ratio test, right? So if we apply the ratio test, we have yeah, so you will have exactly like u to the k plus 1 power over u to the k power. You will just get exactly the limit of this. The limit would exactly be this u, right? And then when this u modulus of u is less than 1/2, so it will converge by the yeah, by the ratio test. Yeah, so the other one will be like a k plus 1 over k over k plus 1 or something, and then when it goes to infinity, k goes to infinity goes to 1. Yeah, so the only thing left is just the modulus of u, right? Because modulus of u they don't have the converge by the ratio test. So since it converges by the ratio test, and also the partial sum is actually less than the partial sum of the red guy, so therefore this is sorry the yeah, so the partial sum of this guy is bigger than equal to the partial sum of this guy, right? And then sorry, the partial sum of this guy is bigger than the modulus of the partial sum inside this guy. So therefore and this one converges, so therefore passing to the limit, right? So this limit must be bigger than or equal to this limit. Okay. So okay. So therefore we have this one. Okay. So yeah, I think one thing that we use here is that the absolute value function is actually continuous. So that you have the limit inside, and then you can pass it to the limit outside. Okay. So therefore, so since 1 over k is less than or equal to 1 over 3 for k bigger than or equal to 3, so we have the modulus of L of u, which is less than or equal to 1 over 3 times summation k from 3 to infinity modulus u to the k's power. So which is equal to modulus u cubed over 3 times 1 minus modulus u, which is less than or equal to 2 over 3 modulus u cubed. Okay, so we just find a upper limit. We'll find an upper bound for this guy. Okay. So and then what happened is that, and then for this one we just do a geometric series sums, right? And so the geometric series sums gives me, so if we pull out a u cubed, right? So it's like a u cubed, and then yeah, so 1 over 1 minus modulus u, right? Yeah. So this u is like the, yeah, so this is the geometric sum formula, right? And then this 3 comes from here. Okay, so this u cube just you can think of the U cubed as a, right? Okay, so it's okay. So and then this is less than equal to that. Wait, so y is less than equal to 2/3. So modulus u is less than 1/2, right? So therefore 1 minus modulus u is so 1 minus modulus u is let's say bigger than equal to 1 minus 1/2. Sorry, just strictly bigger than, right? Which is equal to 1/2. So therefore, 1/1 minus modulus u is less than 1/2. Oh, sorry, less than 2. Yeah, less than 2. Okay. So here, yeah, so we have that. Okay. Okay, so now, let's see. So now we substitute u, which is equal to z over omega. So then it says, so uniformly for z in k, so we have the modulus of capital log of 1 minus z over omega plus z over omega plus z square over 2 omega square is less than equal to 2r cubed over 3 times omega cubed. Okay, so let's see. So okay, yeah. So here we just simply, because this is L of u, right? So L of u is being defined as this guy, right? So when we just replace this u by z over omega, this is just exactly L of z over omega, right? So this is inside, this is equal to L of z over omega. And then, so we will substitute u to be so z over omega is less than, so this inequality estimate requires this modulus u to be less than 1/2, right? And then, so yeah, so I think yeah, I think we can free to erase this equal sign, because yeah, so it doesn't matter if the, yeah, so it just true that there are finally many lattice points satisfying the lattice point is less than the modulus of the lattice point is less than 2 times r. Okay, and then so this is strictly less than. Okay, so okay, so just keep in mind that, so this happens for the tail, right? So yeah, so for these tail factors, yeah. So it happened for the tail. So, yeah, for the tail. And then what happened is that, so here we just replace the modulus of u by modulus of z over omega, right? And then we know that this because this modulus z is less than r, right? Okay, so yeah, so we have that. Okay, so I think maybe I'll just stop here today, and then yeah, so we shall continue next time.